Welcome to lecture 2C of the Computer Architecture and Microprocessor System course. Here we'll be looking at memory elements. I think the previous lecture we looked at using logic gates to construct combinational logic like decoders, encoders, multiplexers. Here we'll be looking at using those same logic gates and or XOR gates to construct memory elements. Combinational logic we looked at previously do not have memory in it. I cannot remember. Once an input comes in and then that input is changed, the previous input cannot be remembered. But we want to build circuits that have some kind of memory elements in them. So we are going to study how memory elements are built with logic gates or with basic logic gates like the AND or XOR gates. Okay, now as said previously, the goal of this course is that at the end of the entire or at the end of the semester, you'll be able to build this single cycle RISC-V processor, a very simple CPU design. And then the CPU design is made up of many components. One of the components is memory. So it's essential that we actually study what memory is made up of. Once we know what memory is made up of, we'll be able to build the individual memory components used in our single cycle RISC-V processor. Now, we have to, in thinking about memory, we have to think about how is one bit stored in a data system. So in a data system, how do we store just one bit? And this storing one bit is what has led to the memories we have today, like the SRAM, the DRAM, the flash memory, and those kind of memories. So the question is, how do we store one bit, and how quick processors went through, or the history of storing one bit is what has led us to have memories we have today. So we are going to go through the attempts people actually looked at in storing just one bit. The first attempt in storing one bit was to use um, an inverter. So here, as you can see, this is an inverter, this is an inverter, and this is also an inverter. So the first attempt was to use three inverters. The inverter of one, the output of one inverter is connected to the input of another in this form, right? And then is this able to store one bit? Now let's see how it operates. Now if the input to this inverter is a 1, then automatically the output to this inverter is a 0, and then the output to this inverter is a 1, and then the output to this inverter becomes a 0, and then the output to this inverter goes to 1, the output to this inverter goes to 0, the output of this inverter goes to 1. Then you see that it follows a trend. You are changing from 1 to 0, 1 to 0, 1 to 0, 1 to 0 within the system. If you consider only this point, it's being changed from 1 to 0, 1 to 0, 1 to 0, and then this is what we call an unstable kind of a device. So even though we'll be able to store a value, but the value keeps on changing from 1 to 0 and from 1 to 0. So you have not been able to store a single value, such as just 1 within the system or 0 within the system. So this is an unstable device, right? Now the second attempt is to use, instead of using three NOT gates or three inverters, we use these two with one, with the output of one inverter connected to the input of another inverter, just like the unstable device. But now we are just using two of them. So what happens in an unstable device? Now if point A here is 0, now point B is 1 automatically. And then if point B is 1, the input of this inverter is 1, the output is 0. Now here you can see that we have been able to store a value, right? We'll be able to store a value. That just means that at point A is just an inverse of point B, right? So point A is just an inverse of point B. So if we store, or if you input a 1 here, the output of this inverter will be a 0, and then the output of this will be a 1. So it's kind of a stable system, right? But you'll be able to store 1 bit or 0 bit within the system. But how to change states is an issue in the system. You can't easily change the state or within uh, this stable kind of device. So we need a way to be able to change the input, so that it will be able to store our 1 bit. So our next attempt is to, instead of using only um, inverters, we connect an OR gate to the input of those inverters, and then we see how it works. And then this is, once we do that, this is what we call an SR latch. So now you'll be able to directly input a value um, with them by stable devices, but the one we just saw previously. We're not able to input values, so that was the main issue. So here, if you have an input here, you have an input here which is S, and then an input here which is R. So you'll be able to give it some values and see whether it will be able to store those values within the system. And then once we configure a circuit like this, is what we call the SR latch, which is the set reset latch. You'll see why it's called an SR latch very soon. Now, the output of this inverter is Q, and then the output of this inverter here is Q bar. The basic rule here is that Q must always be a complement of Q bar. So if you have Q, the output of this inverter must always be Q bar, and then the output of this will be Q. So they are just complements. So the only rule is that Q can never be equal to Q bar. So that is the basic rule. Q can never be equal to Q bar. If Q is 1, Q bar is 0. If Q is 0, Q bar is 1. Once we enter into a state in which Q is equal to Q bar, then you will have a very, very big issue, right? So now how does this SR latch operate? First of all, to look at the operation of the SR latch, we have to first again draw a truth table. In data system, all we do is drawing truth table. You have to pass inputs through the system and see how the output occur. The output are Q and Q bar. The input are S and then R. So now this and OR gate together with um, an inverter is what is called a NOR gate. So we have to also do the truth table of the NOR gate in order to help us figure out the outputs easily, right? So now here, let's start off with if S is 0 and then if R is 1. So what happens if S is 0 and R is 1? Automatically, from the truth table of the NOR gate, immediately any of the input is a 1, the output is automatically a 0, right? If A and B, any of A and B are 1, the output is a 0. So if here is 1, it means that the Q will be 0, right? And then Q bar will be 1. So because a 0 here and a 0 here, 0, 0 in the NOR gate gives you a 1. So Q bar will be 1. That is cool. So now it means that if S is 0, R is 1, Q is 0, and then Q bar is 1. Now what happens if um, S is 1 and then R is 0? So if you have S to be 1 here, automatically Q bar is a 0, because we said anytime any of the inputs is 1, the output is 0. So Q bar will be 0 here, and then once Q bar is 0 here, Q here will be 1, right? So now if S is 0 and R is 0, Q is 1, and then Q bar is 0. That's fine. Now, what happens if S changes from 1 to 0? Now, instead of 1, we have 0 here, and then R is maintained at 0. So now we have S is 0, R is 0. What happens is that immediately S is 0, 1 and a 0 here means that our output Q bar will be 0, and then a 0 and then a 0 here will make our Q1. So as you can see within the system, if S change to 0 and then R is maintained at 0, the previous value or the values do not change. The Q and Q bar do not change. So the values Q and Q bar are maintained if S is 0 and R is 0. Nothing changes. Right. So if S is 0 and R is 0, Q is Q, Q bar is Q bar. Nothing has changed. Okay. Now, what happens if S is 1 and R is 1? So let's go through the circuit. If S is 1, immediately S is 1, Q bar here is 1, right? If R is 1, Q here is 1. Now we have an issue. If Q is 1 and R is 1, our basic rule was that Q cannot be equal to Q bar. But here you have seen that Q is 1 and then R is 1. So the rule has basically been broken. So within the SR latch, once Q is equal to Q bar, the circuit begins to behave abnormally, right? So once Q here is 1, Q is 0, and then Q bar is 0, and then Q is also 0, and then we have an issue, a very, very huge issue. Now, we say that for the SR latch, if the state S is 1 and R is 1 is actually forbidden, that state should not be entered within the SR latch. So if we are designing a circuit using an SR latch, you need to make sure that you never use S and R to be 1 1. If not, your circuit will begin to oscillate or it will begin to behave abnormally. For instance, if S is 1 and R is 1, the values Q and Q bar will be 0 0 here. Now, if we change S to be S to 0 and S to 1, what happens is that Q will be 1 and then Q bar will be 0, and then it will begin to oscillate wildly. It will begin to go to 0 to 1, just like the unstable devices, right? So the state Q and Q bar should never be entered within once you're using the SR latch, right? Now we just call it an SR latch, and then this is the symbol for the SR latch. You have an S and the R here, you have Q and then Q bar as the output. The SR latch truth table is that if S is 0 and then R is 0, we call it, we say the SR is in, the latch is in a hold state. If S is 0 and then R is 1, Q is 0, it means that you'll be able to store a 0 and then Q bar is 1. We said this is a reset state, right? If S is 1 and then R is 0, we'll be able to store a 1 at Q and then the Q bar will be 0, and then this is what we call the set. So that's why we call it the set reset latch, the SR latch. Right now, the main issue with SR latch is that it has a forbidden state, the 1 1 state. You can never enter into that forbidden state. If not, the circuit begins to oscillate if anything changes, right? So we need to, even though you'll be able to store 1 bit using the SR latch, the issue of the forbidden state needs to be eliminated. So how do we actually do that? We use what is called the D latch to eliminate the 1 1 state. All we do is that we connect an inverter to the input R and then connect D directly to the input S. So this is how the configuration for the D latch is. Now with the D latch, once we are going through the circuit, the D latch will not have the state 1 1 anymore. For instance, if you have if D is 0 here, if D is 0 here, the output of the inverter will be a 0 here, and then for the NOR gate, a 0 0 will be the Q here will give us a 0 here, and then a 0 here will give us a 0 at Q, and then once there's a 0 at Q here, a 0, and then a 1 will give us a 1 here. So Q will be 0, Q bar will be 1 if D is 0, right? Now if D is 1 here, if D is 1, the output of the inverter will be a 0. So a 0 and then a 0 will be a 1 here, and then the Q bar will be a 0, and then as long as D is 1, the Q will be 1, the Q bar will be a 0. So if you pass those 1 and 0 through the circuit, anytime there's a 1, Q will be a 0. Anytime there's a 0, Q will be a 0. Anytime there's a 1, Q will be a 1. So you'll be able to store one bit, 1 or 0. So we have an input, you're able to store it. Now there's this circuit can never have the forbidden state. So this is a very good example of how to store a, a one bit, right? So this is what we call the D large. Here, the issue is that we want to be able to control when the Q and then the Q bar output come in. So we have Q here, Q bar. We need to be able to design the circuit that we control the output. For a D large, as long as D comes in, the output becomes available immediately. But we need to have some kind of timing in order to be able to control the output Q and Q bar. We do this simply by using a clock, right? Now, the D latch has been able to get rid of the 1 1 state within the SR latch, but within the same D latch, we are not able to control the output. As long as the input comes in, the output will change. So we need a way to control the changes in the output, and then we do that using a clock. Now the clock is what is shown on the slide. The clock oscillates. It changes from 1 to 0, just like this, from 0 to 1, 0 to 1, 0 to 1, 0 to 1, and then it goes on forever. Now the most important thing is that we have what is called the clock period. From 1, or first of all, we have what is called the edges. This edge goes up, this edge comes down, edge goes up, edge comes down, edge goes up, edge comes down. So this edge is what you call the positive edge, right? And then this edge is the positive edge, and then this edge is what is known as the negative edge, negative edge. Right now here, this point is what we say the circuit is high, and then here is when we say the circuit is low, right? Now from one positive edge to another positive edge is what is known as what is known as the clock period, right? And then in computing the clock period, you can, once you have your clock period, you can use the clock period method to calculate the frequency of your system, right? So the frequency is equal to the 1 divided by your clock period, right? So that is what is used. This is the clock that we are going to use to control the D latch. Yeah. The main aim of using the clock is to control the output of the D latch. You want that this is the D latch as input D, the output is Q. So we want to be able to control when the Q changes based on when D comes in, and then using the clock, because we have the positive edge of the clock, the negative edge of the clock, and then we have the level of the clock here as clock high, and then here as clock low. We can control or determine which portion of the clock to use to control this Q, or when this Q should be stored, right? Or when the D should be made available to the Q, right? So we can store those values at this edge, and then once we are storing values on the high edge or on the low edge, we say This is level sensitive, level sensitive. And again, if you are storing values on the positive edge or on the negative edge of the clock, this is what we term as edge sensitive. Edge sensitive. Right, so we can store values on the level or on the edge. Right. Now, before a value can be stored, this is D, and then this is Q. Now, before D can be stored or D can be made available to Q, right? What happens is that D must be stable. If we are using the high level here, D must be stable for some time before the positive edge of the clock, right? And then, so this is D, this is clock. So before D can be stored, let's say we are using the level here, right? D must be stable for some time before the edge of the clock, right? This time is what you call the setup time. Right? D must be stable for a short period of time before the positive edge of the clock, and then after the positive edge of the clock, D again must be stable for some time before it changes. Right? It must be stable for a period of time before it can change, and this is what we call the hold time. So in the data systems, we have what we call the setup time and the hold time. Before a value can be stored properly, we have a minimum amount of time that value must be stable before the edge of the clock, right? That is the setup time. And then after that value, after the edge of the clock, the value must also be stable for a minimum period of time before the value can change, and then that is what is called the hold time. Right? Now the D latch is constructed by, as we saw previously, by connecting the D to the S and then connecting an inverter to the R. It means that we're using the SR latch, but we're just making the connections from D, connecting D to S, and then an inverter to R. And then this will prevent the SR latch from entering to the 1-0 state. So this is just a kind of recap. So when D is 0, we say that it is in the reset state. So D is 0, Q will be 0, Q bar will be 1. And then when D is 1, we say the D latch is in the set state. So Q will be 1, Q bar will be a 0. We already know what that is. But now we are now going to use the clock. The clock has come into the picture here. So the clock will actually enable or disable a D latch. So if, for instance, the clock, the C here is the same as the clock, it's a 1, the D latch, we say the D latch is transparent. And if the C is a 0, we say the D latch is opaque, right? The D latch being transparent, this means that it allows a value to pass through it, or the value of D is considered, and then the value of D will be latched, or the value of D will be stored, or the value of D will be made available to Q, or the output Q will have the value of D. So that is why that's why we say D is transparent when C is 1. So when C is 1, the D latch is enabled to make any value pass through it, through the D to the Q. Now when C is 0, the D latch is opaque. It means that the D latch is disabled. It means that the value of D is ignored. We don't care about the value of D anymore. And then the previous value that was stored within the system will remain to be stored, right? And then so here we say if C is 0, the D latch is opaque. So you can just draw the true table for that. So as long as C is 0, the previous values that were stored in the large will remain. So it means that the d value that is coming, any d value coming is ignored. And then if c is a 1, the value of d will be made available to kill, right? So here, if c is 1 and then d is 0, kill is 0. And once kill is 0, we know that kill bar is a complement of kill. So it will be 1. And then once c is 1 here, and then d is 1, kill will be 1, and then the kill bar will be a 0, right? So now this is just the operation of the d large. So c simply enables the latch, and then once the latch is enabled, it will be able to let values pass through it. Once c is not 1, and then it means that c is 0, it means that the latch is disabled and no value can pass through it, or the value d is ignored, right? So now we have to you'll be seeing a lot of timing diagrams. This is what we call the timing diagram. You have a clock, you have d, you have q. So you will usually be given the clock. The clock is constant. It goes from 1 to 0, 1 to 0, 1 to 0, and then you'll be given the input d, and then you'll be asked to find what the q is. You'll be able to draw the timing diagram for q. So here you need to know where we are sampling from. So for instance, if you say that this is a D latch, we are sampling using the high edge. The high edge is here. That's where we are sampling. So draw the time diagram for kill based on when D comes in. So let's see how to go about it. Okay, we have our clock. See, okay. The clock moves from 0 to 1, 0 to 1, 0 to 1, 0 to 1, forever. Now we have D. D starts off by being 1, up to 1, up to around here, 1 up to here, then it goes to 0, then it goes to 1, then it's up to around here, 0. You can't write, then it goes here, right? So this is the, now we don't know what Q is, so when the D is the input, so we are using the clock, the high edge of the clock, this point, to store or to make D available to Q, or to store the D, or to sample D. So now first of all you have to first you draw an imaginary line through the positive edges where the storing starts from. Alright. Now the clock is 0. Right? So let's start from 0. Now we are at the high point here, and then we are storing the based on when the level of the clock is high. So here the value of D will appear on Q. So D goes to 1. And then from this point to this point, anytime D changes, the output will also change. Right? If D is constant, then the output is also constant. Right? Right. So here D goes high, Q goes high because D was high, and then it is maintained up to this point. Now this is the negative edge of the clock. At the negative edge of the clock, D is still high, right? So it is maintained. But at this point, D actually changes. But we are the negative, we are at the low edge. Once the clock moves into the low edge, the value of D is ignored, right? So the previous value, which was 1, is still maintained when we get to the low edge of the clock. Now here we have come to another high edge of the clock. Once we get to the high edge of the clock, we look at what D is. D here is 0, so D goes low. Then our Q also goes low, and then it moves on. Now we are still at the high edge, and then D goes to 1. So for here, D also goes to 1, and then it is maintained. Here, D is stable. Now we have come to the low edge here. This is the low edge here. So the value of D will be maintained. So the value of D was 1. It is maintained throughout until we get to another high edge here. We are sampling here. We look at the value of D. D goes to 0. So our value of D will go to 0. And then it goes to 0 forever. So this is the timing diagram, or how Q can be gotten. Very, very easy, right? Okay, so with the D latch, we were simply sampling using the levels here. So you can see that anytime the level was high here, and then the value changes, the D, and then the value D changes, the output also changes. Once it goes to the low level, the value is maintained. Right? So we are sampling using the edges. Now we want to sample using the edges, the positive edge or the negative edge, but not on the level. And then this can be achieved with what is known as the D flip-flops. Now the flip-flops are made with latches. Again, that is just one construction or one way to make a D flip-flop, by using 2 latches. So we are using a D latch, 2 D latches here, D1, 2 D latches, L1 and then L2, right? And then this, once we are using 2 latches, one takes in the input, and then the other latch brings out the output. So it's a kind of master slave kind of flip-flop, right? Now it takes one cycle, one clock cycle, for the output to be made available, for the input to be made available to the output. And this is how it's actually constructed. Our D is connected to the input of the first latch L1, and then our clock is connected to C here. And then you see that the clock for the second latch L2 is connected to an inverter, right? The clock is connected to an inverter before it is connected to the input of L2. And then we have our output Q and Q bar. So what this just means is that if the clock is 1, latch L2 is active or latch L2 is transparent. Latch L2 will allow a value to pass through it. Once the clock is 1, because an inverter is connected to the input of latch L2 will be disabled, and then the input to the latch L2 will be 0 here. So it means if the input here is 0, latch L2 will be opaque, right? So a latch L2 will not allow any value to pass through it, but it will maintain the value it has stored previously. So latch L1 is just the opposite of latch L2. When the clock is 0 here, latch L1 is opaque. It doesn't allow any value to pass through it, and then latch L2 will be transparent. It will allow a value to pass through it. So if we have a value, if we pass a value through D, first of all, the D value will become available to the output of latch L1 when the clock is 1, and after that, the clock must go to 0 before the value can be latched, or the value that was stored in D will appear at the output of latch L2. right? So here, this configuration will allow the circuit, or will allow the timing diagram to be edge triggered, not on level triggered. So now you will be sampling on the edges, but on the not on the level, right? You will see an example soon. So now let's take this example, the same one for the D latch. For the D latch, so this is now a D flip flop. Okay, for this is clock. Now we have X and then we have Q. So X here is the output of the first D latch, and then Q is the output of the second D latch, which is what we actually looking for. But once you're given a circuit like this, you have to first of all find X, because X, as you can see, X feeds into D. So if there's no value in X, or if the value in X has not appeared, then there's no value in the L2 latch. So first of all, you have to draw the timing diagram for X first, before we use the values obtained for X to now determine what the Q is. Now here, the X, these are two latches that have been constructed. So we are using the same idea of the latch to construct this timing diagram. So X is a D latch. So X will be sampling on these edges, right? Edges again. So it means that if X starts from 0, so we are going here. So X starts from 0, right? And then because from the configuration, X is a D latch. Once the clock comes in and then the clock is high, the clock high will enable L2 latch, and then the value will be stored. So D comes in here, D will be high here, and then that will be maintained at this point throughout the level, and then it comes here, it's still 1, 2 to be maintained. Here it changes, but because we are going to low, it will be maintained until we get to another high point here. So here D is 0, so it goes to 0, comes here, D is 1, so it goes up here, and then comes here. Here has come down, so it move on until it gets to here, right? And then it comes down here, right? So this X is just the same as the D latch we saw. So because this is still, they are still, this is still a D latch, so the X would just follow the output of the D latch. Now let's look at Q, right? So now Q is taking the value of X based on the clock, but because we have an inverter connected to to the input of L2 latch, it means that now if the clock is low, that is when D gets sampled, right? So if clock here is 0, that is when the output inverter becomes 1. So now let's take note of that. If the clock is low, so this is the point we are sampling our Q, right? When the clock is low, then the value of D will be sampled by Q, or the value of D will pass to Q, or the D latch, the L2 D latch will be transparent for it to pass X to it, right? So now first of all, we start off with 0 here, right? Now we come to the high point here. Now, as I said, now we are sampling on the low edge, so the value here is maintained to 1 until we get to here, right? So here's 1 until we get to the low, the negative edge of the clock, or when the clock goes low. So here is where we sample our Q. So here we look at what x is 1. So here it goes to 1, right? And then it's maintained. Then we have to look at, we are looking at x, so we have to look at what is x. So x goes to 1, right? Down here x has changed, but we are at the positive edge, or we are at the high edge, so the value of Q is maintained because we are always sampling on the low edges. So this will be maintained until we get to this point, which is the low edge of the clock, this point. Now at this point we actually have to look at the value of x again. The value of x is still 1, so that value is maintained. From this point to this point is maintained. We get to the high point. The high point is where the value is maintained again, so we get to another low point, which is here. And then at this low point the value of x is 1, right? So now this goes to 1, and this is what we get, right? So here, this is the operation of the D flip-flop, and then this is what we care about, the Q. So now here, as you can see, um, uh, from the configurations here, the Q is usually sampled using the negative or the low edge of the clock, right? Just on this edge, that is when it is sampled. You see here, there were a lot of changes here, but all those changes were ignored, and then it gets sampled on the negative edge here. It sampled this one, and then this point is sampled this one. So this is how easily you can draw your timing diagram for Q. So this is the D flip-flop, and then we say that the D flip-flop is edge triggered, right? As you can see, the value was made available, or the value was sampled only at the negative edges of the clock, right here, based on the configuration, based on this flip-flop design. So you have to look at the design of the flip-flop. What is important is that the X here gets sampled when the clock is high. So when the clock is high, X gets sampled. Now when the clock is low, that is when Q gets sampled, because we have an inverter connected to the input of L2 latch. So this is the timing diagram for the flip-flop, right? Now the D flip-flop is actually used to store just 1 bit, and it stores the 1 bit actually perfectly based on the edges of the clock. We'll be able to control it to store the value based on the edges of the clock. But because the D only stores one value, we need to know how to store many values, right? So is that we want to store a 4-bit number, 5-bit number, 6-bit number. So how do we actually store a 4-bit number, a 5-bit number, a 6-bit number, whatever? So all we have to do is that we use the same configuration of the D flip-flop, but we use a number of the D flip-flops based on the number of bits we want to store. So if you want to store a 4-bit number, we use 4 D flip-flops. If you want to store a 32-bit number, we use a 32-bit we use 32 flip-flops. So this is just how it is configured. So if you want to store 4 bits, we have D0, D1, D2, D3, and then the clock will be connected to all the D flip-flops, right? So this will enable you to store a 4-bit number, and then for easy in a circuit, you don't draw all the flip-flops, but you draw what looks like this. You have 4 bits. Anytime in the anytime you see something like this. It means that this is multi-bit. It means that it's more than 1 bit. If you see just a line like this, it just means it's 1 bit, a 1 bit line. So you just use this one to indicate that it is multi-bit. It's several lines interconnected to it, right? But if you see only one line, it just means 1 bit, right? So here the 4 bits. To store 4 bits, we just use the symbol is just this, and then this is the clock, and then we have our input here, input which is 4 bits, and then we have our output which is also 4 bits, 4 bits, and then this is a 4-bit register, right? Now to have a 32-bit, you just have to change this to 32, and then here is 32 bits. Our output too is 32, and then this will just be called a 32-bit register. But you must take note that inside a 32-bit register, there are about 32 flip-flops in there. So that's just what you must take note of. Alright, so now that you have seen how to store multiple number of bits using our basic logic gates, and then now using flip-flops, we want to see what a register file is. And then a register file is part of our single site processor. So if you know how or what is inside the register file, you'll be able to design a register file, and then in the long run, we will connect the register file to the ALU of our single site processor. So let's see how the register file looks like. So this is what is called the register file. Right. So this register file, anytime you see the symbol that is a register file, and then this register file has two outputs, QA and QB, right? So we see that it is a dual read port register file. It means that we can read from two locations at a time. We can read from QA and we can read from QB. Now this register file has only one input, right, which is DW. And then we see that this register file is a single write port because we have only one write, and we can only write to only one port here. Right, now we see that this register is a 32 by 32 register file. What do we mean by the register file is a 32 by 32 register file? It just means that inside the register file there are a number of registers, right? And then this number of registers number from 0 to 31. So there are 32 registers within the register file, and each register file has a data width of 32 bits, right? So the data width of the register file is 32 bits, and then the number of registers inside the register file is 32. That's why we have a 32 by 32 register file. Now here we have W, which is the write enable. We have write address. We have read address A, and then we have read address B. We'll see what all this means in a few seconds, right? Now, first of all, what is inside this register file? Let's see how to construct or what to construct what the register file is actually made up of. So the first thing is there are registers within the register file, and then these registers, each location is 32 bits. So this is register 0. So there are a number of registers. If you're designing a 32 by 32 register file, so it means that you have a total of 32 in number, right? A total of 32 register files from register 0 to register 31. Now you will have to have a way to um, read from this register files, and then we have to find a way to write to this register files. So how do we write to one register file at a time in this configuration? So we have 32 of them, right? Register 0 up to register 31. So to write to each location of the register file, we need what is known as a decoder. We saw the decoder design in combination logic. So this is we need a decoder. And what the decoder should have 32 outputs, right? So each output of a decoder connects to one register file. Each output connects to one register file, and then the last output will be connected to register 32, register 31, right? Now, if you have a 32 output decoder, that means that we actually saw that 2 to the power n output of a decoder is equal to n inputs, right? So the decoder will have n inputs, and then if 32 is 2 to the power 5, so our output, our input to the decoder will be equal to 5 bits, right? So we need 5 bits to be able to address the 32 locations in our decoder, which each one of them will be connected to the one register file. So it will be a 5 by 32 register or a 5 by 32 decoder, right? So this decoder will be used to enable us to write to one location. So for instance, if you want to write to location 0, the 5 bits here will have to be 0, 0, 0, 0, 0, 0. And then once we have 0, 0, 0, 0, 0, the output 0 of the decoder will be activated, and then all the rest will be 0. So here will be 1, and then you'll be able to write to just this single location, right? Now here, the address is what is known as the RW, so the write address, right? RW is just write address of the register file, and then the write address is just the input to the decoder, our 5 to 32 decoder, or our 5 by 32 decoder. Right. Now, how do we read? Now, you have seen how to write to the registers, but now we need to also read from the registers. There are register 0 to register 31. Now we can only read from one location at a time, right? So it means that what we need another circuit or another component to be able to take all the inputs and then bring out only one output, and then this we do with a multiplexer. We've already seen what a multiplexer does in combination logic. So all the outputs, all the outputs of the registers will be connected to this. So it will be register 0 up to register 31. So there's 31 of them, and then we have only one output, right? But then, so we have a 32 multiplexer by 1. But then the most important is that we need a select line, right? To be able to address this 32 registers. So the select line will also be 5 bits. We have already seen that if you have 32 inputs, the select line will have to be 5 bits to be able to address the 32 registers. So the select line will be 5 bits here, and then this 5 bits, if you want to read from register register 0, you have to make sure that this select line is 0, 0, 0, 0, right? And then register 0 will be routed to the output. If you want to read from register 31, you need to make sure that the 5 bit is 1, 1, 1, 1, 1, and then register 31 will be routed to the output. So we use the multiplexer to read from one. We use the multiplexer to read from one register file, or to read from one register within the register file, right? So now here, the select signal is what is called the RA. So read address A. Now, because we have in our previous configuration, we have the register file to have two read ports. We need another multiplexer to route the signals again. So we need two multiplexers in order to be able to read from two registers at a time, right? So we just route the registers to another multiplexer, and then we just have another select line, which is also 5 bits, which will be RB. This is known as the read address B. So once we want to read um, register, once we want to read register R0 from QA, we just give the select here 000. We want to read register R1 through QB, we just give the select 0001, and then it will be routed. So we'll be able to read from two locations at a time. So this is what we do. We need a multiplexer for that, right? Okay, so that's the simple implementation of a register file. We have used D flip-flops to be able to store the bits. We've used a decoder to be able to write to each port, and then we've used a multiplexer to be able to read to each port, right? So that's just a symbol for a multiplexer. Register file. Now the register files are really fast because they are usually smaller in number, right? We don't use the register file to store a lot of bits, but we use it because the register files are located within the CPU itself, and then we just need small numbers of them to be able to store computational data um, in them, and then the register files are actually usually connected to the ALU, the arithmetic logic unit. So the outputs of the register files are connected to the ALU, and then the ALU can actually write back to the register file. Right now, adding ports to the register file is just straightforward. You just need another multiplexer. But the issue is that we can have the register file does not scale. We can't store a lot of bits in it. For instance, if you have a 32 megabit register file, it means that you need a very huge multiplexer and then a very huge decoder. And then we know that we are using logic gates to actually design these multiplexers and then these decoders. So, and then we know that each logic gate also uses a transistor. So if you're using a 32, if you're designing a 32 megabit register file, you need about 32 by 1 million to 1 multiplexer, and then 32 by 20 to 1 million decoder. That is a lot of logic gates, and then that translates to a lot of transistors. So the register file cannot be used to store so much data. We need another kind of memory to be able to be able to do that. And then within our single cycle processor, we have the register file which is connected to the ALUs, and then we also have memory. So we are going to see what is inside the memory or what makes up the memory. The memory is used for storing a lot of data, but the register file is used for storing just a small amount of data. So let's see how we store so many data within our memories. So in this single cycle processor, we have two memories, one for storing the instruction and then one for storing the data. And this is just the Harvard architecture, right? So one memory is used for storing instructions or the operational code of the CPU, and then one is used for storing computational data of the CPU, right? So now the thing is, how do we actually build large memories if we're not using the register files? Now, yeah, we have to come up with a concept of or a concept. If we have a shared line, instead of using multiplexers and then decoders and stuff like that, we are using the same flip-flops, but now this those flip-flops will not be connected to multiplexers or decoders and stuff like that, but they will be connected to a shared line, right? So the most important is that one flip-flop will be able to drive one shared line. So that's how basically we start off to build large memories, right? So you have from D0 here to D10. So these are our flip-flops, and then the flip-flops are connected to a shared line, and then one flip-flop can only drive one shared line, and then we need the tri-state buffer. We already looked at that. The tri-state buffer will be connected to all of the flip-flops, and then if any flip-flop want to send data to the shared line, it ought to enable its tri-state buffer, and then the value will be made available to the shared line, and all the other values or all the other flip-flops will be disabled. Right, so we just use a tri-state buffer and connect them to the flip-flops, and then we've already looked at the truth table of the tri-state buffer. We say that if the if the enable is 0, the output is at high impedance, or the high output flows, nothing connects to it. Um, if the enable is 1, then the value of D will appear, or the value of D will be routed to the output. Right, so that's just how the tri-state buffer works, which we have already looked at. So now for large memories, we have large memories are usually arranged by, or you can read from large memories by using what is called the address. Okay, so once you buy any memory, whether it's SRAM or DRAM, you will have it look like this, right? And then you have the address line here, and then you have the data line. The data line is usually double edged, meaning that it's dual ports. You can read and write from the data line. So here is data, but the address line is only one port, right? Then we have N here, and then this is the address line. So to write to the memory, you have to give it an address, and then you give it data, and then it will give the value, the data value will be written to that particular address within the memory. And then to read from the memory, again you give it an address, and then the value within that memory or that memory location will be routed to the output. Right, so that's just how we read and write to large memories, right? So now if you have a memory, it is usually, if you have a memory like 4 by 8, right? This just means that we have 4 megabytes by 8 8-bit data, or 8 bits memory. So what this means is that in data systems, you might already know that we have megabytes, we have um, kilobytes, megabytes, gigabytes going, and then the kilobyte just means that 2 to the power 10, right? The megabytes just means 2 to the power 20, and then gigabytes means 2 to the power 30. So if you have 4M by 8 memory, it just means that we have 4 by 2 to the power 20 by 8 bit memory. And what this means is that we have address lines here. This is address, and then data, right? So it means that each location of of our memory stores 8 bits, right? And then it also means that we can, the address line is 4 times 2 to the power 20, which is 2 to the power 2 times 2 to the power 20. And then our address line is this plus this, the 20 plus 2. So our address line is 22, right? This again means that we have 22 address lines, and then the total number of locations within the memory is um, 4 times 2 to the power 20, right? So 2 to the power 2 times 2 to the power 20 and 2 to the power 22. So this is the total number of locations within the memory, right? So this is just a 4 megabytes by 8 bits memory. That simply means that we have 22 address lines for this 4M. We have each location is 8 bits, and then the total number of locations within the SRAM is 2 to the power 22. Right? 2 to the power 22 locations within the memory. So that is what we mean by a 4M by 8 memory. So typically, this is how the memory configuration or the memory looks like. We have 4M by 8 memory. It means that our data input is just 8 bits. It means that each location stores 8 bits, um, as you can see here. And then we have 22 address lines here. Now the output too is also 8 bits, because once the input is 8 bit, the output follows the input. The output is the same as the input, so it's also 8 bits. And then we have additional signals like the chip select and write enable. The chip select will enable the memory. We have the write enable that will make sure that for you to be able to write in location, the write enable must be high before, or the write enable must be 1 before you can write. If the write enable is 0, you cannot write to a location. So to write to a location, you have to pull the write enable signal high, and then you give it data, and then you write. And then the output enable is also available. The output enable just means that you want to read from the memory, and then if you want to read from the memory, you just give it an address and give it an output enable, and then the value within the memory will be made available to the output. So this is just how the memory looks like. Now, how do we design a 2 by a 4 by 2 memory model? So the 4 by 2 memory model just means that um, we have 2 address lines. So we want to design a simple 4 by 2, or what we want to see what's inside a 4 by 2 memory, right? As I said, this indicates the address line. You can use this one to compute your address line. You can use the first value again to compute the number of locations within your memory. Now, and this is the data width. You can use this to compute your data width. Um, So it means that this memory just means that we have the data width of 2 bits. So each location can store 2 bits. And then this means that we have a total of 4 locations. The 4 here just means we have a total of 4 locations. Location 0, 1, 2, 3, 4 locations. And then once we have a total of 4 locations, we need 2 to the power 2 bits here to be able to address those 4 locations, right? So the address bits here will be just 2 bits. Right, so we have 2 bits address, we have 2 bits data width. The number of locations is 4, so we have 4 locations. So that is the simple. If we want to design a 4 by 2 memory, we have an address line of 2. So that's why you see here our address line is 2. We have our data. We have our data with here 2 is 2. So D in 1, D in 2. And then we have our output 2 will also be 2. The output always follows the input. So once we have a 2-bit input, we have a 2-bit output, right? Again, you have a write enable and then an output enable. So this will be the configuration of what is inside the 4 by 2 memory model, right? We have because we have 4 lines. These four locations are known as the word lines. These four locations, what is known as four lines. So it means that each location will be using a D flip flop. So we are using D flip flops within um, within each location, right? So here our address line is 2, our output, we have our write enable, we have our output enable. So down here, if I want to actually write to any of the locations here, for instance, I want to write to address 00. So I'll have to write to location 000. I have to input 00 to the address here, and then this 00 will activate this line here, right? Right. This zero will activate this line, and then once my write enable, as you can see, once my write enable is also one, the flip flops within this line, the flip flops within the first location will be activated, and then the value I put in here will be stored within or to location 00 here, right? To also read from this memory, give it an address. For instance, I want to read from location 3, so give it address 1111 is 3. Give it address 11, and then the 11 enable will enable this AND gate, and then you have to use an output enable also. So an output enable comes in together with the one value here, and then this flip flop, these two flip flops will be enabled, and then you'll be able to read or the values in within these two flip flops will be made available on the D01 and then D02 line. So this is what um, the memory, the 4x2 memory is made up of. And then for the 4x2 memory, or inside the memory, we have what is called the word lines, right? And then we have what is called the bit lines. So word lines, the bit lines. Now what the word line do is that the word line will enable the flip flops, and then the value that is within the flip flop will be made available to the output. That's what the word line does. The word line enable the flip flop for the value that is within the flip flop to be made available. The bit lines will also enable the flip flop for which to be able to write to it. So to write to the flip flop, we need a write enable. So those bit lines are used to enable the flip flop for which to write to any location within the memory. Right. Right. So next thing is the typical SRAM cell. This is how a typical SRAM cell actually looks like. The typical SRAM cell is made up of, this transistor is the NMOS transistor, right? And then we say that for the NMOS transistor, a one applied to the gate of the NMOS transistor will close the transistor, or will enable the transistor, and then a value can be passed through it. If we pass a 0 to the gate of the transistor, then the transistor will be disabled. So this is the configuration, or what an SRAM look like. It is made up of about 8 transistors, right? So this transistor is one transistor. This is another transistor. We know that an inverter is made up of 2 transistors, as we have seen earlier. This is the design of an inverter. It's made up of 2 transistors, one NMOS, PMOS on top, and then an NMOS at the bottom. And then we have an input, and then we have our output. So it means that each transistor is made up of, each inverter is made up of 2 transistors. So for a typical configuration of an SRAM, it is usually made up of about 6 or 46 transistors, right? So this is 2 plus 2, 4, 5, 6 transistors, but there are other configurations that uses more transistors. So we say that it requires about 4 to 6 transistors based on how you are going to design it. Now with the typical expression, we have the word line. The word line is connected to the inputs of the NMOS, and then these NMOS are called the path transistors, because once the word line is one, it will allow any value to pass through it, right? And then we have what is called the bit line. The bit lines are connected to the outputs or to the drains of the NMOSes, right? So if um, to either to read from from the transistor, you have to enable the word line. The word line is pulled to one, so that the value that is within that is within the SRAM will be made available to the bit line. The bit line, we have B and B bar. This B is a complement of the B bar here, right? So now to read from the SRAM, all you have to do is that you have to enable the word line, connect the word line to one. Once you connect the word line to one, the value within these two um, inverters will be made available to the B line, right? So if you have a zero here, once we connect the word line to one, the value zero will be made available here. If you have a one here, it will be made available to the one here, right? Now to write to the SRAM, all you have to do is that you have to pull the word line high, right? So once the word line is high, you now put the value that you want to write on the baseline. So if you pull this word line high, you put the value you want to write to the baseline. You want to write to the SRAM on the baseline, and then that value will be made available to the inverters, and then it will be able to store it, right? Okay, so now the SRAM, to design an SRAM, we design SRAMs using smaller. We design bigger SRAMs using smaller SRAMs, right? Now, for instance, if I have a 4M by 8 SRAM, I can design this for I want to design a 4M by 8 SRAM. Okay. So I have an SRAM which is 4M by 8. I want to design this 4M by 8 SRAM using a 4K by 1024 SRAM, right? This 4K by 102 SRAM is smaller than this 4M by 8 SRAM, but I want to design this one using a combination of this 4K by 1024 SRAM. So how do I go about it? That's what we are going to see now. So now the basic question is that, how many 4K by 1024 SRAMs can I use to design a 4M by 8 SRAM? Now we already know that if you have a 4M by 8 SRAM, it just means that I have a data width here is 8 bits, right? And then the total number of locations within this SRAM, this total number of locations within the SRAM is 2 to the power 2 times 2 to the power 20, which is equal to 2 to the power 22. So 2 to the power 22 is 4194304. So I have a total of 4194304 locations within my SRAM, and then each location stores 8 bits. Now if I have a 4K by 1024, all that means is that our data wave here is 1024, and then I have total locations is 2 to the power 2 times 2 to the power 10. K just means 2 to the power 10, right? So it's 2 to the power, it's 2 to the power 12, and then 2 to the power 12 just means that I have a memory, the total number of locations is 2 to the power 12, which is 4096 locations, right? 4096 locations within 4K by 1024 SRAM, and I have 4194304 locations within a 4M by 8 SRAM. So now, first of all, what you have to do is how many within within the 4K by 1024. You have, as I said, this is each location is 1024 here, right? So how many bits from the 4M by 8 SRAM can be stored in one location of the 4K by 102, right? And then because I have my 4M by 8, it stores 8 bits at a location, all I have to do is I take 1024 divided by 8, and then I'll have 124 divided by 8 is 128. So 128 locations here, 128 locations within my 4M by 40 will be stored in just one location of my 102 4K by 1024 SRAM, right? Now after I've gotten the number of how many locations is stored in one SRAM, it just means that 128 locations within my 4K will be stored in one location of my SRAM. So it means that if I have a total of this 4K by 1024 has a total of 4096 locations. So 4096 locations will be equals to what? How many locations can this one store here? So to be x is equals to 4096 times 128, which is equal to 524, I think 288, right? Right. So now I have 524,288, right? So 5288 locations here can be stored in just one SRAM. So if I know this value, and then I know that the total number of locations within my 4M by 8 is 4194304, all I have to do is I take 4194304, and then I divide it by 524,288, and this will give me the total number of locations, or the total number of 4K by 8, 4K by 1024 SRAMs I can use to design a 4M by 8 SRAM. So if I do this calculation, I'll have 8. So I will need 8 4K by 1024 SRAMs in order to be able to design a 4M by 8 SRAM, right? So here we have 4M by 8 SRAM. I'm using a 4K by 1024. I will need, first of all, we will need a decoder, a 12 by 4096 decoder, because we have 4096 locations in each SRAM. So 4096, we will need 12 bits to be able to address 4096 locations, right? And then we need a multiplexer to select each location within the 4K by 1024 SRAM, right? And then because we have a 1024 output from the SRAM, we are connected to the multiplexer, we need 10 bits to be able to address the 1024 um, um, SRAM outputs. So the 10 bits is just the select line for the multiplexers. And then I will need 8 of them. So 1, 2, 3, 4, 5, 6, 7, 8. So I'll need 8 of this one to be able to design my 4 by 4M by 8 SRAM, right? I can have other signals, connect other signals like the chip select, that will select, or that will enable the chip, and then the write and read enable, right? Now we can also construct really huge memories by combining our 4M by 8 SRAM, and then usually the SRAM, this is how the SRAM actually look like. SRAM has banks. We have the bank 0, bank 1, bank 1, bank 2, bank 3, bank 4, up to a number of banks, and then each bank is made up of smaller SRAMs, right? So that is how the internal picture of the SRAM simply looks like. And then to select each bank, we need a chip select. Right? The chip select will enable one bank at a time. All right. Okay, now after looking at the SRAM, another very large memory is the DRAM, the dynamic RAM. The SRAM just means static RAM, the dynamic, and then the DRAM is called the dynamic RAM. So you will see the DRAM is made up of, as you can see on the slide, a capacitor which is connected to the ground, and then the pulse transistor, and then the pulse transistor is connected. The gate of the pulse transistor is connected to the word line, and then the drain of the pulse transistor is connected to the bit line. Right, so that's just how a DRAM looks like. So this DRAM can store, this configuration can store 1 bit within the D line. But how does it actually store the value? So if you want to store anything within this configuration, all we have to do is that we have to pull the word line high. So if the word line is high here, and then we put the value we want to store on the bit line. If it is a 0, we will put a 0 here. If it is a 1, we put a 1 here. And then once this is high, this circuit will be closed, and then the value here will pass to the transistor, to the value here will pass to the capacitor, and then the capacitor will store whatever charge or was made available on the bit line. Right now, that's easy. Now to read from this DRAM, all you have to do is, again, you pull your word line high, put a 1 here, and then it will enable this pass transistor, which is our NMOS, and then the value here, any value that is stored, if it's a 1, then the 1 will discharge to the bit line, right? So any value here will be made available on the bit line. So the difference here between the SRAM and then the DRAM is that the SRAM is using a capacitor. So what happens is that anytime you read from a capacitor, the capacitor is drained, right? The charge within the capacitor is drained to the bit line here. So if there's a 1 here, and then you pull the word line high, and then the value in the capacitor will be discharged to the bit line. That value is lost. So what happens is that within the DRAM needs to be refreshed constantly. Anytime you read from the DRAM, you have to refresh the DRAM, or you have to refresh it to bring back the value. So you need another circuit in a way that once you store a value within the DRAM, that particular value is stored somewhere else, so that anytime the DRAM is read, the volume within the DRAM is read, you have another configuration that will actually bring back the value to the capacitor, or that will actually recharge the capacitor. So it means that the DRAM needs a constant refresh anytime there's a read. So that is a very that is that is the that is the difference between the SRAM and the DRAM. You know that the SRAM, we're using at least 6 transistors, but within the DRAM we're using only 1 transistor. So that is an advantage of the DRAM. The DRAM is smaller than the SRAM, because to store just 1 bit, the SRAM needed 6 transistors, while the DRAM needed only 1 transistor. The only disadvantage within the DRAM is that it needs extra circuitry for it to for me to bring the value back, because anytime you read a value from the capacitor discharges and the value is lost. So we have to constantly refresh it, and constantly refreshing the DRAM leads to the use of more power than the SRAM. So it means that the SRAM uses less power than the DRAM, because the DRAM needs constant refresh. So that's just the difference between the SRAM and the DRAM. So that you know how the DRAM is made out of, or the configuration of the DRAM, and you know how the SRAM is also made. And then you know the difference between the SRAM and the DRAM. That's the end of this lecture. Thank you.